applied logarithmic models. So now we're talking about like real life uses of logarithms. So logarithms are useful for measurements ranging from very small to very large, and there are three that are pretty common: the intensity of sound, pH levels of substances, and magnitude of earthquakes. So we're going to do an example of each in this order. So first, intensity of sound. Sound is measured in decibels. The loudest football crowd ever recorded was 137.6 decibels. What is this danger threshold in terms of sound pressure in pascals? So pascals is what sound pressure is measured in. By the way, 137.6 decibels is dangerous for your ears. I think it's like if you're in that sound for more than 15 minutes, you could actually have like hearing damage. Just FYI. Okay, so we have this like formula. This is the loudness here. This is your decibel reading. So loudness equals 20 times the log of the pascals is P divided by 2 times 10 to the negative fifth. And this, the label of this answer would be in decibels. Okay, so we know the answer is decibels. So when I get this 137.6 decibels, that's like the loudness, right? So that's L. So I'm going to take 137.6 equals 20 times the log of P divided by 2 times 10 to the negative fifth. Okay, so I need to isolate the log piece. So my first step is to divide both sides by 20 to isolate the log of the pascals over the 2 times 10 to the negative fifths. So 137.6 divided by 20 gives me a 6.88. Now, how do we solve a logarithmic equation? Well, I change it to exponential. So the base of this is a common log, so base is 10. So I'm going to take 10 raised to the 6.88 power, and that will give me P over 2 times 10 to the negative fifth. Well, if you want, you can take 10 to the 6.88 power. But our next step, right, is going to be to multiply both sides by 2 times 10 to the negative fifth. So I'm going to have 10 to the 6.88 times 2 times 10 to the negative fifth. And this is going to equal my pascals. Now, you can just type that into your calculator just like that, right? If you do, you have 10 raised to the 6.88 times 2, maybe put this in parentheses, times 10 raised to the negative fifth. And you're going to get your answer, which is, number of pascals is 151.7, okay? You could also use your exponential rules. Because these have the same base, we could add the exponents. So you'd have 10 to the 1.88 times 2. Either way, these are equivalent, and your answer is 151.7. Let's deal with pH. Golden Delicious apple juice has a pH of 3.8, in case you didn't know. What is the hydrogen concentration of the apple juice? Round to 4 decimal places. Okay, so this is our formula. pH equals negative log of the hydrogen concentration. So the hydrogen concentration is the argument of the logarithm. Now here we are given the pH of 3.8, so I just plug that in where I see pH. So I have negative log of the hydrogen concentration equals 3.8. So my first step is, again, to isolate the log. So I'm going to divide both sides by negative 1. Because 2 negatives will give me a positive hydrogen concentration, and this would give me a negative 3.8. Okay, so how do I solve a logarithmic equation, right? Because I want to isolate the hydrogen. Well, again, I have a base 10. So base 10 raised to the negative 3.8 power gives me the argument, which is the hydrogen. So if I type in 10 to the negative 3.8, I get 1.5849 times 10 to the negative fourth. Goes on and on and on and on and on. But if we want this as a decimal, remember changing scientific notation to decimal notation means negative 4, I'm going to move my decimal 4 places to the left. 1, 2, 3, 4. And that's where my new one's going to be. So if I round this to 4 decimal places, 1, 2, 3, 4, 5 tells me to round up, it would be 0.0002 would be my hydrogen concentration, or that rounded to the nearest 4 decimal places in scientific notation. Okay, let's do an earthquake example. Earthquake A, we're going to do a comparison of two earthquakes. So these are two earthquakes that happened in San Francisco a long time ago. I don't remember the years. But earthquake A was an 8.3 on the Richter scale, and earthquake B was a 7.0 on the Richter scale. How much more intense was earthquake A than earthquake B? Okay, so these are the magnitudes. Magnitudes are on the Richter scale. And these I's represent the intensity of the earthquakes. So like how much stronger? Was it 2 times, 3 times, 4 times? So when you look at these, 8.3, 7.0, you might say, well, it's just 1.3 more. Can't really be that much more intense. But friends, let's do the math and check this out. So we are going to plug in our Richter scale numbers into those magnitudes. So the magnitude for earthquake A was 8.3, and the magnitude for earthquake B was 7.0, and that equals the log of A over B. So what we're trying to find here, just to reemphasize, we're trying to find this whole piece, the argument, because it's the intensity of earthquake A compared to that of earthquake B. Okay, so just bear with me here. Okay, so 8.3 minus 7 is 1.3, gives me the log of the intensity of A divided by the intensity of B. To solve a logarithmic equation, again, we have a common log, base 10. So 10 to the 1.3 equals the intensity of A over the intensity of B. Now, 10 to the 1.3 power, if you plug that into your calculator, you get like 19.95. So we're going to round to 20. So we have 20 equals intensity of A over the intensity of B. Now, if I want to isolate the intensity of the earthquake A, I would multiply both sides by the intensity of earthquake B. That means the intensity of earthquake A is 20 times the intensity of earthquake B. So you can say that it's not that far apart on the Richter scale, but this 8.3 was 20 times more intense than the 7.0. So it's only 1.3 more on the scale, but the intensity of it, because of how they are measured, because these are such big, booms, for lack of a better word, earthquake A is 20 times more intense than earthquake B. So kind of fun, of different ways that we can play with logarithmic models.